Hello and welcome to this clip on oxidation numbers and redox reactions. We'll go through what reduction and oxidation mean and the fact that when they happen simultaneously it's called a redox reaction. We'll take you through how to assign oxidation number using the oxidation number rules and look at what the roles of an oxidizing agent and a reducing agent are in a redox reaction. We'll then have a look at some examples and then show you how to use oxidation numbers to show or demonstrate what species have been oxidized or reduced in a reaction when you get the balanced equation provided. This is the way it's commonly found in examination questions, so it's worth trying a couple at the end of the clip. So the easiest way to remember which is which, in terms of oxidation and reduction, is the oil rig mnemonic, which is oxidation is loss of electrons and reduction is gain of electrons. Obviously, if something loses electrons, something else is to gain them and vice versa, so both processes have to occur at the same time. So when this takes place, you get what's called a redox reaction, redox being a shortened version of reduction and oxidation put together into one word. So what exactly is oxidation number? The oxidation number of an element involved in a redox reaction basically refers to the number of electrons that atoms of that element have involved in bonding to atoms of a different element. And it's really important that you remember it's bonding to atoms of a different element. So in these cases, oxygen and nitrogen are not combined with atoms of other elements. So any uncombined element is always considered to have an oxidation number of 0. The carbon atom in carbon dioxide, by contrast, has 4 electrons involved in bonding to oxygen. And because the oxygen is another element, the carbon has an oxidation number of +4. And each oxygen atom in carbon dioxide has 2 electrons involved in bonding to another element. So in this case, carbon is the other element. So the oxygen atoms each have an oxidation number of -2. And the reason that it's +4 and -2 is because the more electronegative atom always gets the negative oxidation number. And the sum of all the oxidation numbers in this neutral molecule add up to 0. So using that idea, can you pause the video and try and work out the oxidation number of each element here? You've got to remember the oxidation numbers must add up to 0 if the molecule is neutral. Both these molecules are. And the more electronegative element gets the negative oxidation number. So hopefully you had those numbers in mind. Boron has 3 electrons involved in bonding. It's the less electronegative element out of boron and fluorine, so it takes +3 oxidation state. Fluorine has 1 electron involved in bonding. It's the more electronegative element out of boron and fluorine, so it takes a -1 oxidation state. Similar story for sulfur and fluorine in SF6. So it's time now to have a look at some of the rules we have to apply when we're assigning oxidation number. I've just given you a little taste of it in this slide, but there are actually a set of rules that you need to know. So let's have a look at them. So why don't you pause the video and try this one. It's an ionic lattice, or part of an ionic lattice, and again the oxidation numbers must add up to 0. The lattice is neutral, calcium oxide is a neutral compound. So the more electronegative element gets the negative oxidation number. And bearing in mind that ions have the same oxidation number as their charge, that'll make this very easy. So that must mean that calcium 2+ has a +2 oxidation number. It has 2 electrons involved in an ionic bond. The oxide ion, O2-, also has a -2 oxidation number. It has 2 electrons involved in an ionic bond. So the oxidation numbers must add up to 0 if the lattice is neutral. +2 and -2 is 0. The more electronegative element, in this case oxygen, gets the negative oxidation number. And the ions have the same oxidation number as their charge, which is what's happening here. So let's now have a look at those oxidation number rules I mentioned a minute or so ago. So the oxidation number of an element that's involved in a redox reaction basically means the number of electrons that atoms of that element have involved in bonding to atoms of a different element during that reaction. there are some fundamental rules that we have to apply when we're assigning oxidation numbers. First rule is that all uncombined elements have an oxidation number of 0. Every single atom in a compound will have an individual oxidation number. So every oxidation number that's assigned will have a sign, as in negative or positive, plus or minus, which is always written before the number. So we always write, for example, +1 and not 1 plus. So obviously this only applies to compounds and ions, because 0 has no sign. So uncombined elements don't get a plus or a minus because they're automatically 0. If you have an ion made of a single element, such as chloride, for example, that will have an oxidation number equal to its charge. If you have an ion that contains more than one element, such as carbonate, the combined oxidation states of all the elements must add up to the overall charge. So that means in carbonate, the combined oxidation states of the carbon and the 3 oxygens must add up to 2 minus. And in a neutral compound, the oxidation states must add up to 0. So it might be worth pausing the video clip and jotting all these down, and then we can continue. So there are also some fundamental assumptions we apply to certain elements when we assign oxidation numbers. Hydrogen, when it's combined with another element, always gets an oxidation number of +1 within that species. Oxygen in the same situation gets an oxidation number of -2. And fluorine, when combined with another element, always gets an oxidation number of -1. So the one exception for hydrogen is where it occurs in a hydride, such as in sodium hydride. So there's one exception for oxygen as well, and that's in peroxides. The commonest peroxide you'll come across at A level is hydrogen peroxide, and here the oxygen has an oxidation state of -1 instead of -2. And you'll be glad to know that there's no exceptions to the rule for fluorine. There's a couple more examples I need to give you before we go any further. So all group 1 elements, when combined, have a +1 oxidation state. All group 2 elements, when combined, have a +2 oxidation state. That's easy enough. In the vast majority of cases that you come across, the only exceptions being when they're combined to oxygen or fluorine, the other halogens, such as chlorine, bromine and iodine, have an oxidation state of -1. So, obviously quite a few things I've asked you to take on board in a fairly short space of time. Let's try some examples to get our heads around this a bit. So grab a piece of paper and jot these down. Pause the video clip and see if you can try and do them. Come back in about 5 or 10 minutes. There will be some that are harder than others, because I put them in there on purpose, obviously. But if you pause the clip and come back in a little while, we'll see how far you've got. So in the first one, carbon dioxide is a neutral compound, so the oxidation states must add up to 0. We know that each oxygen atom gets an oxidation state of -2, but because there's 2 of them, that's -4 in total. So as such, carbon must have an oxidation state of +4. So to help me think my way through this, I write the oxidation numbers above each element, or above the symbol of each element, in the formula of the compound. In the case of water, again it's a neutral compound. The oxygen atom gets an oxidation state of -2, and the hydrogen gets an oxidation state of +1, following the oxidation number rules we just looked at. There are 2 hydrogens, so together they add up to +2, and the overall charge is therefore 0. So we can put the oxidation states above each of the atoms in the formula. So you can see the pattern with sodium oxide as well. We're using the fact that sodium is in group 1 to give it an oxidation state of +1, and we know that oxygen automatically gets an oxidation state of -2. So Na2O2 is an example of a peroxide. Sodium always gets an oxidation state of +1 because it's a group 1 element. So if you work this through, There's two sodiums, so together they add up to +2. For the overall charge to be 0, you have to have -2 to balance +2. However, how are you going to do that if you have oxygen taking -2 and there's two of them? That would make it -4. So for this to work, oxygen has to have an oxidation number, an oxidation state of -1. So this is an example of what we call a peroxide. It's an exception to the rule for oxygen. So by now you should find HCl quite straightforward. Again, it's a neutral compound, so the oxidation state must have to 0. Hydrogen gets an oxidation state of +1, so that means chlorine must have an oxidation state of -1 for the overall charge to add up to 0. So F2O is a rather exceptional one as well. I wanted to see if you could work this one out. Maybe it was a little mean of me not to mention it in the previous slide, but it is another exception to oxygen being -2. It's really the only exception because fluorine is so much more electronegative than oxygen. It forces oxygen to take a positive oxidation state. So let's now have a look at some examples of assigning oxidation numbers to ions. So see if you can jot these down, pause the video, and then work out what the individual oxidation states might be this time. So the first thing to remember is that the overall charge must equal the sum of the oxidation states. So you start with what you know. You know that the oxygen atom in each case will have an oxidation state of -2. So when you have multiple atoms of the same type, you have to multiply the oxidation number of each atom by the number of times it appears. So in carbonate, the oxygen adds up to a total of -6 because there's 3 of them, -8 in sulfate because there's 4 of them, -6 in nitrate because there's 3 of them. So in the case of carbonate, that must mean that the carbon has an oxidation state of +4. And we can apply oxidation numbers in that way. So in the same way, we can assign +6 to sulfur, +5 to nitrogen, and +1 to chlorine. So sometimes we use Roman numerals to actually name a ion. So we put in brackets a Roman numeral after the name to tell us what the oxidation state. So we'd have carbonate, sulfate 6, nitrate 5, and chlorate 1. And because oxygen's oxidation state is always -2, we don't put it in the name. So in the same way, we can assign +6 to sulfur, +5 to nitrogen, and +5 to chlorine. And I've underlined the 8 part of the name because that's the part that tells you that oxygen is in the ion somewhere. So when looking at a reaction and trying to work out what's been reduced or oxidized, you have to assign oxidation states to every single element and then see what's changed. So if your oxidation number has become more positive, electrons have been lost and therefore it's been oxidized. If the oxidation number has become more negative, it's the opposite, electrons have been gained and therefore it's been reduced. So for hydrogen, there's no change at all. For carbon, it's gone from -4 to +4, so it's clearly been oxidized, electrons have been lost. And for oxygen, it's gone from 0 to -2, but it's turned to -2 in 2 separate species, so in both cases it's actually been reduced. So we can therefore call this a redox reaction, because we've been able to use oxidation numbers to show what's been reduced and oxidized. So when we're looking at reducing and oxidizing agents and trying to work out which is the reducing and which is the oxidizing agent, all we have to do, once we've worked out in the reaction like we've just done what's been reduced and what's been oxidized, is decide what loses electrons and therefore something else will gain them. So the reducing agent will lose electrons, be oxidized in other words, so another species can be reduced. And simultaneously the oxidizing agent will gain electrons, in doing so be reduced, so another species will be oxidized. So to go over that one more time, a reducing agent will cause another species to be reduced by losing electrons to that species. An oxidizing agent will cause another species to be oxidized by gaining electrons from that species. So pause the video on this screen and see if you can work out which is which in this particular reaction. What I've done is I've taken an image that actually shows you what's oxidized and what's reduced. So sodium has been oxidized because its oxidation number has become more positive, but chlorine has been reduced because its oxidation has become more negative. So sodium will be the reducing agent, it lost an electron and caused chlorine to be reduced. Chlorine is the oxidizing agent, it gained an electron and caused sodium to be oxidized. So can you do the same thing here? Pause the clip and see if you can work it out. So in the first one, Cu2 plus is the oxidizing agent. Its oxidation number goes from +2 to 0, so it's reduced, so something else gains the electrons. So magnesium's oxidation number goes from 0 to +2. It's lost electrons, so that means something else must have gained them. So to fully understand this second one, you need to maybe convert it into an ionic equation. Cl2 plus 2I minus gives you I2 plus 2Cl minus. So that's chlorine reacting with two iodide ions. So chlorine is the reducing agent, chlorine is the oxidizing agent because it itself has been reduced. And the iodide ion is the reducing agent because its oxidation state has become more positive, which means it's been oxidized and therefore the chlorine has been reduced. So to recap, chlorine is the oxidizing agent because it's caused iodide to be oxidized. The iodide ion is the reducing agent because it's caused chlorine to be reduced. So let's now have a look at this in exam style questions. The first question says, use oxidation numbers to show that strontium has been oxidized in this reaction. The best thing to do at this point is to put in the oxidation numbers for everything like we looked at before. And I'm actually going to make the page a little bigger to give us some room to do that. So what you need to do now is draw a little line from the element on one side to the same element on the other. So we'll start with strontium. So this is the technique you used, or you need to use. You state what's been oxidized. You state what its original oxidation state was. And then you finally state what its new oxidation state is and in what species. So to clarify that in another way, you say what's been oxidized, in this case strontium. You say that it was in oxidation state 0 in strontium metal. And then finally what its new oxidation state is and in what species. So let's move the page down a bit. And you can see quite clearly that the next question is asking us to do exactly the same thing, but also to balance as well. So the balancing of that equation and the completion of that equation should be straight out of GCSE, so I'm not going to dwell on it. But I'm going to do the answer to the second part, which is exactly the same idea as what we just looked at. So calcium has been oxidized from oxidation state 0 in calcium metal to oxidation state +2 in calcium chloride. So let's have a quick look at the mark scheme. It's quite straightforward. We said what the oxidation number was originally, and we said what the oxidation number was in the final species. We balanced our equation, getting both parts right, and we did the same thing again in our second answer. So in a nutshell, that's how you put it together in exam questions. Hopefully this has been a reasonably useful introduction to redox and oxidation numbers, but if you've got any queries, jot them down, bring them into one of us in the subject extension at college, or maybe go in and have a chat to your teacher. But in the meantime, thanks for your time and patience, and see you soon.